Okay, so I'm going to go make the video of what we started in class on Thursday, May 2nd, just so that you have a recording of the same thing. And so what this section is about is how deformation actually in metals occurs when specific planes slide past one another under a shear action when that shear stress is big enough to overcome what we might think of as the friction between the two planes. And so I can call this the slip plane. I'm going to go ahead and erase that stuff I had just put there, just so that it's not confusing. So that's my slip plane. And this is the direction of the force. There is a direction, we'll say it's like here. That's my slip direction. And the slip plane has a perpendicular a line that's perpendicular to the plane. So this is called the slip plane normal, meaning the perpendicular to the slip plane. All right, and I'm going to define a couple of angles here. The angle between the force and the slip plane normal is phi, and the angle between the force and the slip direction is lambda. All right, so with all these things defined, I have an equation for the resolved shear stress. Shear has a tau for a symbol. Resolved shear stress, that's equal to the applied stress times cosine of phi times cosine of lambda. That's phi cosine phi cosine lambda. All right, that will give me the force that's resolved into that slip system, that plane in that direction. And if I'm going to give, let's see, I want to be consistent to what I did in class. I called the slip direction the ABC direction. The slip plane was the DEF plane, and the normal to that plane would be the DEF direction. And then I said that the force or stress is applied in the X, Y, Z direction. All right, so if I give those directions letter names, just so that we can come up with a general equation, and then you can plug numbers in. Cosine of phi, that's the angle between the slip plane normal and the slip direction. Cosine phi is going to be equal to d times x plus e times y plus c times z divided by the square root of d squared plus e squared plus f squared times the square root of x squared plus y squared plus z squared. So notice that there's a different color here. For cosine phi, it's the cosine of the angle between the slip plane normal, DEF. So there's my D, E, and F. That should be an F. So D, E, and F come from the slip plane normal. There they are in my equation. And then X, Y, and Z come from the the force direction of the stress, X, Y, Z. So there's the X, the Y, and the Z coming from the direction of stress, X, Y, and Z. All right, and then the equation for the cosine of lambda, it works just the same way. My slip direction is ABC, so this is going to be A times X plus B times Y plus C times Z divided by square root of A squared plus B squared plus C squared times the square root of X squared plus Y squared plus Z squared. This is the equation. If you're given two vectors, A, B, C, and X, Y, Z, this is the equation to find the angle between them. Again, notice that this A, B, and C come from the slip direction, A, B, C. And the X, Y, Z, just as before, comes the XYZ here comes from the XYZ in the force direction. All right. Okay, so we can go ahead and skip that slide and come up to this one and do the first example. So in this case, I want to know the resolved shear stress for one slip system of a BCC material. So my slip direction, that was our direction XYZ. Let's call that 1, 2, 3. The 1, 2, 3 direction. X, Y, Z. And we're choosing one plane in one direction for BCC. BCC is going to have the slip planes are of the type 1, 1, 0, and the slip directions are of the type 1, 1, 1. So let's choose for our slip. I want to use different colors here so we can see where different things are coming from. So I'm going to call the slip plane, and that was in our example, that was DEF. So I'm going to, and it should be of the type 1, 1, 0. So I'm going to make that be 1, 0, 1. That's one of the 1, 1, 0 type planes. And this will be given to you. And then the slip direction we'll use, let's use 1 bar, 1, 1. Okay, and I know that 1, 0, 1 is in, 1 bar, 1, 1. That direction is in the plane 1, 0, 1 because 1 times negative 1 plus 0 times 1 plus 1 times 1 equals 0. The dot product is 0. Okay, so I've given all of my directions actual units, and I'll go ahead. Let's see, we said the plane is the 101 plane, and the direction is the, oops, let's see, can I just erase that? No. Normally I put the direction column right next to it. So if my plane is 101, my direction is 1 bar 1 1. All right, so cosine of phi, cosine of phi is going to be, I want to use my colors here so we can see where the numbers come from. It's going to be 1 and 0 and 1. That comes from my plane. And then x, y, z, this is times 1. This is times 2. This is times 3. So these number 1, 2, 3 come from here, the direction of the applied stress, and the 1, 0, 1 comes from the plane. And then that whole thing is divided by the square root of 1 squared plus 0 squared plus 1 squared, comes from the plane, times the square root of 1 squared plus 2 squared plus 3 squared. So that whole thing is good. I've got 1 plus 0 plus 3. So the numerator is 4 divided by the square root of 2 times the square root of 9 plus 4 plus 1, 14. So 4 over root 28. And that is I didn't calculate that. Let's do that. So that's equal to 0.76. Okay, and then my equation for cosine lambda here is going to be, again, I'm going to use the colors hopefully to help you see where the numbers are coming from. So my direction is 1 bar 1 1. So there's my 1 bar, 1 and 1. And then I'm going to multiply that by the vector for the force. And that was 1, 2, 3. All of that divided by the square root of negative 1 squared plus 1 squared plus 1 squared times the square root of 1 squared plus 2 squared plus 3 squared. So that's equal to, negative 1 plus 2 is 1, plus 3 is also, again, 4 over the square root of 3 times the square root of 14. That's 0.62. So the product of the two is 0.47. And multiplying that by the applied stress of 50 megapascals means that the resolved shear stress, that's this column, last column, is going to be 23.6 megapascals. Okay. All right, so that's an example where I've just given one slip system. That's one here, 101 plane, 1 bar, 1 1 direction. I'm just asked to calculate the resolved shear stress on that one slip system. All right, take it up a notch, a little bit more complicated. In this case, we want to look at all of the slip systems on one plane. And so I chose I guess, I don't know if we got to this in class, but I posted a handout that has these values in it. I chose a plane of, let's see, I want to use blue for a plane. I chose the 1 bar, 1 plane. This is FCC. So the slip planes are the 111 type, and the slip directions are the 110 type. So calculate the resolved shear stress for all the slip systems on the 1 bar 1 plane that are caused by the applied stress of 70 million psi in the last time I used the 1, 2, 3 direction. This time I want to say it's 2. Let's see, I want to make it black here. This is going to be on the 2, 0, 1 bar direction, the applied stress. So the first column is the slip plane, and we said that's going to be the 1 bar 1 plane. And there's 3 directions that are on that plane. And they're all of the type with 110. So I got a 110 type and a 101 and a 011. And I need to add negative signs as necessary to make the dot product 0. So this first, oh my gosh, these should be not planes, but directions. Oh, I put these, gosh, this should go here under direction. For this first direction, 110, if I look at the dot product, I have 1 times 1 plus negative 1 times 1 plus 1 times 0. That is 0. I don't have to change that. The second direction that's on the 1 bar 1 plane will have a 1, 0, 1, the 0 in the y place, and I'll make the first 1 negative so that the dot product's 0. And then the last direction I'll put 0 where the x place is. And this one's fine. It's I've got 0 times 1 plus 1 times negative 1 plus 1 times 1, that's 0. So these are the 3 directions on the 1 bar 1 plane. All right. Now, cosine of phi, I might be able to fit it on here. I'm probably not going to I'm going to do it all in one color though. This will be, remember that my stress direction is 2, 0, 1. So I've got 1 times 2 plus negative 1 times 0 plus 1 times negative 1 divided by the square root of 1 squared plus negative 1 squared plus 1 squared times the square root of 2 squared plus 0 squared plus 1 squared. So that's all equal to my numerator 2 plus 0 minus 1. So my numerator is 1. Denominator is square root of 3 times the square root of 5. So that's equal to 1 over the square root of 15. It's 0.26. All right, I'm going to not write it out here when I solve for cosine lambda. Just know that I'm going to be using directions and the stress direction. So this is going to be 1 times 2 plus 1 times 0 plus 0 times negative 1 divided by the square root of 1 squared plus 1 squared plus 0 squared. That's the square root of 2 times the square root of 5. So 2 over the square root of 10. 0.63. For the second slip system, I've got negative 1 times 2 plus 0 times 0 plus 1 times negative 1 divided by the square root of 3 times the square root of 5. So we have a negative 3 over square root of 15. And that's 0.77. All right, and then the last, for the 0, 1, 1 direction, I've got 0 times 2 plus 1 times 0 plus 1 times negative 1 divided by the square root of I've got an error here. This should be square root of 2. All of the direction cosine lambdas should have the same denominator. So this would be square root of 2 times square root of 5. So negative 3 over the square root of 10. Is 0.95. All right, now back to this. I've got 0 times 2 is 0, plus 1 times 0 is also 0, plus 1 times negative 1 is negative 1. Square root of 2, square root of 5. So this is negative 1 over the square root of 10. So this is negative 0.316. Okay, so now for this next column, I take the product of the cosine phi times the cosine lambda. So this is 0.26 times 0.63 0.16. And then 0.26 times 0.95 negative is 0.25. And then 0.26 times 0.32 negative is 0.09. Okay, so the resolved shear stress is the applied stress, which was 70 million psi, times cosine phi cosine lambda. So this is 70 times 10 to the 6 psi times 0.16. So that's 11 times 10 to the 6 psi. And the next 70 times 10 to the 6 times 0.25 negative. So that's 17.5 negative, 17.5 times 10 to the 6 psi. And the last case, I've got 0.09 times 70 times 10 to the 6 is going to be negative 6.3 times 10 to the 6 psi. And so if I'm only considering these three, I'm going to have deformation happening first where the magnitude is highest. So of these three slip systems, failure will first occur in the 1 bar 0 1 direction. Okay. Now this last example is one where I'm looking at all 12 slip systems. So I've got an FCC, a single crystal. So that means that the slip planes are the 1, 1, 1 type. Didn't really need to do a bracket within a bracket. So this is the 1, 1, 1 type planes and the, let's see, go like this for the family of directions 1, 1, 0. So there's 4 of these planes, and on each there's 3 directions per plane. So for the first set of 3, I'll use the plane 1, 1, 1, and the directions will be 1 bar 1, 0, and 1 bar 0, 1, and 0, 1 bar 1. All right, so cosine phi, we're given that the stress is in the 2, 1, 2 direction. So I've got 1 times 2 plus 1 times 1 plus 1 times 2. That's 5 divided by the square root of 3 times the square root of 4 plus 4 plus 1 is square root of 9. So that's equal to 0.96. All right, cosine lambda for the first slip system, I got -2 plus 1 plus 0. So this is a -1 of the square root of 2 times the square root of 9. For the second, -2 plus 0 plus 2, this is 0. And for the third, 0 times 2 is 0, minus 1 plus 2, this is plus 1. So let's get the decimal equivalent. So this is -0.24, and this is positive 0.24. So cosine phi, cosine lambda for the first, I've got 0.96 times 0.24. And that's 0.23. And this is negative. For the second, because cosine lambda is 0, cosine phi, cosine lambda is 0, and the last one, it's positive 0.23. So I have 75 megapascals applied stress. So for the first slip system, 0.23 times 75. So this has got 17.3 megapascals, and it is negative. Second is 0, and third is positive 17.9 megapascals. All right, so either the first or the third subsystem, they both have the highest, they both have high, they both have the same resolved shear stress, just opposite sign. Right? I'll write this down. Okay, so I advance here, and my values for cosine phi, cosine lambda times the applied stress, this was negative 17.3 megapascals. This was 0, and this was positive 17.3. And this was for the 1, 1, 1 plane. The one bar 1 0 direction, the 1 bar 0 1 direction, and the 0 1 bar 1 direction. Okay, so now we're ready to look at the next slip system. I'm going to say 1 bar, 1, 1. And so my three directions are going to be 1, 1, 0, and 1, 0, 1, and 0, 1 bar, 1. All right, so cosine phi for the second set, remembering that my force is in the 2, 0, no, sorry, this is the 2, 1, 2 direction. Two, 1, 2 direction. Okay. So cosine phi is going to be -1 times 2 plus 1 times 1 plus 1 times 2. So that's 1 divided by the square root of 3 times the square root of 9. For the 1, 1, 0 direction, it'll be 2 plus 1 plus 0, so 3 over the square root of 2, the square root of 9. For the 1, 0, 1 direction, I'll have 2 plus 0 plus 2, so this is 4 over the square root of 2 times the square root of 9. And for the third direction, I've got 0 minus 1 plus 2, so this is 1 over square root of 2, square root of 9. So this is 0.23. 0.71 is up here. And 0.94 is here. And so we multiply cosine phi times cosine lambda. This here is 0.19. So this is, the product is 0.14. This is 0.18. And 0.19 times 0.23. This is 0.04. And again, my applied stress for this example was 75. Yeah. So 75 megapascals times 0.14 is 10.5. Point 18 times 75. This is 13.5 megapascals. And finally, this is 3 megapascals. Okay. So we had negative 17.3, and then 0 and then plus 17. And then we just had a 10.2 and a 13.5 6 and a 3 megapascals for the second set. All right. So now let's look at the 1 bar 1 plane. And the directions we'll choose, I've got 1 1 0, 1 0 1. I need to make one of these negative, and 0 1 1. Don't need to make any of those negative. Again, remember my stress direction is 2 1 2. So for the 1 bar 1 plane, cosine phi would be 1 times 2 minus 1 times 1 plus 1 times 2. So this would be 3, and then divided by the square root of 3 times the square root of 9. For cosine lambda, I've got 2 plus 1, 3 over the square root of 2 square root 9. Here I've got minus 2 plus 0 plus 2, this one's 0. And finally, 1 plus 2, this is a positive 3 over square root of 2 square root of 9. All right, so for my cosine phi, that value should be 0.58. This is 0.707, 0 and 0.707. And so my resolved shear stress values are 0.58 times 0.707 Oh, wait, we just did that. I'm sorry. I've got cosine phi cosine lambda. So I just need to multiply that by 75. So this is 53. Let me just point out, I'm doing 0.707 times 75. So that's equal to 53. That's 0, and this is 53. So now that is the highest value. Just checking to see if I get the same thing as I did before. 3 over root 27, yeah. And looks like it. Let's just check. 3 over root 27 that's right. 3 over root 18. Okay, hold on here. This is 0.707, so it's that. So then this column will be 0.58 times 0.707. That's 0.41. And this is also 0.41. So the resolved shear stress should have been this should be 31, and that one should be 31. Okay, so that's 3 of the planes. All right. So my values here, -17. This is the shear stress, resolved shear stress, and that's in megapascals. So I got -17, 0, plus 17, then 10.2, 13.6, and 3, and 31, 0, and 31. And finally, we'll use the plane 1, 1, 1 bar. And the directions, let's see, we got 1 bar, 1, 0, 1, 0, 1, and 0, 1, 1. Those, the 1, 0, 1 and 0, 1, 1 have a dot product of 0. I don't have to add any negative signs. And again, my stress is in the 2, 1, 2 direction. So cosine phi is 1 times 2 plus 1 times 1 plus 1 times -2. So this is numerator of 1 over the square root of 3 times the square root of 9 equals 0.19. All right. For the first direction, I've got -2 plus 1 plus 0. So that's -1 over root 2 root 9. -0.24. For 1, 0, 1, this will be 4 over root 2 root 9. And this will be 3 over root 2 root 9. So this is 0.94 for that second slip system on this plane. And for the third, this is 0.707. So the product of cosine phi and cosine lambda, this is -0.05. This is 0.18. And then 0.707 times 0.19. This is 0.13. So you multiply that by the applied load, which was 75. So So 0.05 times 75. This is negative 3.8. Then 0.18 times 75. This is 13.5. And then 0.13 times 0.19. This is 0.0. No, I don't need to do that. I need to be 0.13 times 75. So this is 9.8. Okay? And so the failure, we got all these slip systems. The first to be activated are these two that both have a applied resolved shear stress of 31. And I don't know where the math error is, but there should be symmetry here, so this would have the same value as this. These two the same. These two the same. Yeah, this should be 10.1. Okay. So it's very tedious, I'll give you that, but basically what we're doing here with this third example is we're finding the resolved shear stress for every slip system, and we're looking for where that value is the highest.